let's start. So today we're very happy to have Hanlin from IIS to talk about the hardness of range avoidance and proof complexity generators from Demi-Bits. Let us give a round of applause.
Thanks for the nice introduction. And actually today I'm not going to talk about proof complexity generator, but mainly about the range avoidance and derivative. And this is a joint work with Chen and Yan, and I also included something in the independent and concurrent work of Rahul Lango. And please stop me for any questions if you have any. So around 50 or 60 years ago, cryptography was in the dark age. We don't really know whether there are meaningful crypto, let's say, against time-bounded adversaries. In fact, we don't even know that this is the right question to ask. And we also didn't know whether cryptography can do anything beyond encryption and decryption. And this changed since the pioneering work in the 70s, where we discovered that there are indeed some reasonable cryptography that seems plausibly secure against time-bounded adversaries, and we formulated basic primitives such as one-way functions. And we also know that there are something beyond secret key cryptography. For example, we can do key exchange over public malicious channels, and we can do public key encryption, and we can do much more. After 50 or 60 years of work, we now have a very beautiful picture of all kinds of cryptographic primitives. But this is not the picture that I'm going to talk about. I'm going to talk about another dark age. The dark age is about cryptography against the non-deterministic adversaries. If you look at this thing, you might not even be convinced that there should be cryptography against non-deterministic adversary at all. For example, if I have a one-way function, then a non-deterministic adversary is always gonna guess the secret seed behind the image, and then the non-deterministic adversary can always break a one-way function with certainty. So it's even unclear whether the phrase cryptography against non-deterministic adversaries makes sense or not. And also, even if this thing makes sense, what can we do? Why is cryptography against non-deterministic adversaries interesting? Fortunately, we are not in the dark age now. A pioneering work of Rudich showed that, at least in some sense, we can define meaningful notion of cryptography against the non-deterministic adversaries. And at least in my opinion, such cryptography could plausibly exist. Rudich defined some primitives called superbits and demi-bits, and I think they are arguably the fundamental primitives in the picture of cryptography against non-deterministic adversaries. But unfortunately, this is pretty much what we know so far. And in this work, we are going to extend the boundary of such cryptography a little bit further. And there are some very interesting phenomena happening in this map that is unique for non-deterministic adversaries. I hope to convey to you.
Is there a reason you're calling it cryptography against non-deterministic adversaries instead of cryptography against non-deterministic adversaries?
It's shorter.
Okay. But then
it's a very good question.
Then it's more clear what it should be.
Yeah, that makes sense actually. Yeah, perhaps I should have called it crypto against non-deterministic adversaries. And in this talk, we are going to look at some phenomena in cryptography against, let's say, non-deterministic adversaries. And this seems to be unique in the sense that it heavily uses the fact that our adversaries are non-deterministic or non-deterministic. And our proofs are actually very simple. And I'm going to talk about the full proof in this talk. And actually not just one proof, but two. Because when we finished our proof, we thought it was really simple. and only to discover that Raffo-Lango had an even simpler and even more beautiful proof. But let's see what will happen. First, let me talk about this cryptography against the non-deterministic adversary and why this notion makes sense. We all know what are pseudo-random generators against deterministic adversary, right? So if I have a generator that stretches a short random seed into a long pseudo-random string, we call it a pseudo-random generator if like time-bounded adversaries cannot distinguish between true random strings and outputs of the pseudo-random generator. In particular, for any adversary A, the probability that A outputs 1 on a true random string and the probability that A outputs 1 on a pseudo-random output of the generator should be negligibly close. And this is the classical definition of pseudo-random generators. A naive way to define pseudo-random generators against non-deterministic adversaries is to just replace deterministic adversaries with non-deterministic adversaries. And one can easily see that this doesn't work because there is always the seed guessing attack. The non-deterministic adversary given an input y can just guess a seed z and see if g of z is equal to y. If it is, then it accepts. Otherwise, it rejects. So this adversary will output 1 on true random strings with probability very close to 0, because true random strings are not likely to be outputs of G, but it will always output 1 on a pseudo-random string. So it always breaks the PRG in this sense. However, non-determinism is not, or at least not known, to be closed under complement. And you cannot say that I have a non-deterministic adversary and it rejects if there exists a seed, except if there's no. At least there's no immediate way of doing this. So maybe one can conjecture that no adversary can reverse these numbers. What does this mean? It means that we conjecture that no adversary can output 1 with a significantly higher probability on true random strings than on pseudo-random strings. So let's say that G is a super-bit generator. If for any non-deterministic polysize adversary A, the probability that A outputs 1 on true random string cannot be much larger than probability that A outputs 1 on pseudo-random string. And it's very crucial that we put no absolute value here, and the order of these two quantities are also crucial. But if you don't want to deal with this definition, or you don't like super-bit generators, then it's also fine, because we are not going to talk about super-bit generators anymore. We are going to talk about a weaker primitive demi-bits generator. We say that a generator G is a demi-bits generator if there is no non-deterministic polysize adversary A that accepts a large fraction of random strings. The 1/2 here is kind of arbitrary number, and rejects every possible output of G. This primitive is weaker than super-bits generator in the sense that any super-bits generator is also a demi-bits generator. And I hope this will be a little bit easier to understand. You can think of an adversary for breaking demi-bits generators as a proof system trying to prove that some given string is not in the range of G. And if G is a secure demi-bits generator, then this means that any proof system that you can come up with cannot efficiently prove non-range for all but just a little fraction of strings. Let me also introduce the notion of cryptographic proof systems, because I feel I personally am more convenient talking about proof systems instead of non-deterministic adversaries, but they are essentially the same concept. A proof system or a cryptographic proof system is just a non-deterministic algorithm for, let's say, tautology. Tautology is the class of circuits that can be satisfied by any assignment, and the the language of tautologies is the canonical co-NP complete polynomial. Here is a more precise definition. A co-correct proof system is a deterministic algorithm with a verifier that gets a purported tautology phi and a purported proof pi, and accepts if pi is a proof that phi is indeed a tautology. And we require that first we runs in polynomial time in the total length of the tautology and the proof. Second, for any tautology, there is at least one proof that can prove that phi is tautology. This is called completeness. And there's no limit on the length of the proof. In most proof systems that we study, every tautology has a brute force proof of length 2 to the n. And finally, for every phi that's not a tautology, there should be no proof that can convince we that phi is a tautology. This is called soundness, that is, we cannot prove anything that's false. And maybe an immediate question after you see this definition is whether there are proof systems where any tautology phi has a polynomially long proof pi that proves it. And this is true if there exists a proof system that this is true if and only if NP is equal to co-NP. So if you believe NP is different from co-NP, then any proof system should have hard tautologies. And the goal of proof complexity is just to find like given the proof systems that we are interested in, find tautologies that are hard for this proof system. For example, you can study proof systems like this, where every PQR are just circuits. And turns out that we don't know how to prove low bounds for such kind of proof system. But anyway, I think I just want to tell you about this definition, and it's essentially equivalent to non-deterministic algorithms for tautologies. And I will use proof systems in the rest of the talk because I find it more convenient. That is, the definition of Demi-Bits generator can be rephrased in this way. For every proof system P, there are only a small fraction of Y such that P can efficiently prove Y is not in the range of G. A good picture to have in mind is you have this is the space of all length L strings, all possible outputs of G. And the real outputs are just a tiny fraction of this whole space. Everything outside the range of G, they're outside the range of G, right? But for any efficient proof system, what this proof system can recognize to be outside the range of G is, again, just a small fraction. And this is the definition of Demi-Bits generator. Any questions so far? Good. So I just gave you a definition of some cryptography against the non-deterministic adversaries. But is it plausible? Let me give you one candidate that I'm very interested in. This is the so-called truth-table generator. This generator takes the description of a size Sn circuit as input and outputs the truth table of the circuit. If Sn is slightly less than 2 to n, let's say 2 to the 0.1 n, then this is stretching in the sense that it stretches a short description into a long output. And also, this is the generator underlying all the circular bound, like proving that some function is not in the range of this generator. It's equivalent to proving a circular bound for that function. So given our limited progress in circular bounds, we should expect that this is a hard generator in some sense. Rudich, in his 1997 paper, conjectured that the truth table generator is a Demi-Bits generator. I didn't specify the parameters here, but I think for most reasonable parameters, this seems like a plausible conjecture. This conjecture can be also like phrased in equivalence terms, like any proof system cannot prove random circular bound tautologies, or something like there is no non-deterministic natural proofs, something like that. Well, the plausibility of such conjectures, I think, is a subjective issue. But if you ask me, I think it's pretty plausible. And next, I think I want to talk about some motivations for study cryptography against non-deterministic adversaries. Why is it interesting or why is it useful? In fact, I think motivations for studying this is not fully justified yet. So we are still only seeing very limited research on superbits and demi-bits. But I hope that I think there are a lot of more motivations for studying this, and we need to discover more of them. For me, maybe the most compelling motivation is to study the hardness of proving circular bonds. Again, some history. In the 70s, complexity series started to study circuit complexity. The hope was that circuits are just combinatorial objects made of and or not gates and trying to compute functions. So maybe by like very hardcore combinatorial analysis, we can prove lower bounds against circuits. But turns out that this is a very hard problem, and even today we don't have good circular bounds. We don't even have any explicit function or explicit. You can take explicit means single exponential time or something. We don't even have any explicit function that we can prove requires circular complexity larger than 10. So we are really stuck at this front. So it's natural to study why we cannot prove circular bounds. Or maybe more precisely, fix your favorite proof system. And I think we should study why this proof system cannot prove circular bounds.
Wait, sorry, can you say something about the difference between these two statements? Because I got a little confused when you were talking about the truth table generator, because we can prove circuit lower bounds for random truth tables, but not in this. What you're saying, not in this read to text sense. Is that right?
Yeah. So what the proof system really needs to do is, I hand you a truth table. I promise you the truth table is randomly generated, but the proof system needs to produce a proof that this particular truth table is hard. It requires large circuits. Thanks for the question. So we only know that random truth tables are hard by counting arguments, but we don't know where the hard truth tables are. And even if I just write down a bunch of random bits now and ask you to prove that, oh, this function requires this much circuit size, I think it looks hard, right? Yeah, and I think that's the point. I believe that the necessary assumptions and the tools for studying the unprobability of circular bounds lie in this picture of crypto against non-deterministic adversaries. It's just my belief and my motivation. Another motivation for studying crypto against non-deterministic adversaries is that it's related to hardness of range avoidance and more generally hardness of de-randomization in some sense that I will clarify later. The range avoidance problem is the following problem. You are given a generator that stretches n input bits to L output bits. And your goal is just to output any string that's not in the range of this generator. And you can see that if n is smaller than L, then a random string of length L is not in the range of this generator with good probability. So you can say that there is a good randomized algorithm for solving the range avoidance problem. You just ignore the input and output some random string. Previous work also showed that deterministic algorithms for range avoidance would imply important consequences in complexity theory, like they would imply breakthrough circular bounds and so on. But so deterministic algorithms for this problem is of great interest, but these results also don't say whether deterministic algorithms should exist or not, since they only show that a deterministic algorithm for range avoidance implies some, for example, circular bounds, which are things that we believe, but we just don't know how to prove. Perhaps a bit naive question you can ask is whether you can de-randomize this randomized algorithm, maybe using the same assumptions that used to de-randomize BPP. If you know this line of work by Nissan-Wilson, Impagado-Wilson, then you know that good circular bounds suffice to de-randomize BPP. But turns out that you cannot use a similar kind of assumption to de-randomize range avoidance because it's unclear how to verify your answer is correct. So given a y, you want to verify if y is not in the range of C, this problem is NP-complete. So the de-randomization assumption can actually give you a list of strings, and you can guarantee one of them is it's not in the range of C, but you don't know how to select this one. And the hardness of range avoidance against deterministic algorithm was initiated by Rahul. And he had this thought of how do you, like, if you want to prove hardness results for deterministic algorithm, how do you differentiate between deterministic algorithms and randomized algorithms? And his idea was that if a deterministic algorithm is guaranteed to be correct, then let's use it as a subroutine in non-deterministic algorithms and use hardness assumptions against the non-deterministic algorithms to derive hardness of range avoidance. You can also, at least in principle, I think you can also replace range avoidance with any other problem where a random solution is good with high probability, but it's unclear how to verify the solutions. And at least, I think at least in principle, you can apply ideas from crypto against non-deterministic adversaries to prove that such algorithms cannot be de-randomized. But let's go back to range avoidance. With some work, Rahul and other people like Jiatu Li, Ryan Williams, and Eli Chen showed that the range avoidance problem is hard for deterministic polytime algorithms if NP not equal to co-NP and some crypto assumption called indistinguishability obfuscation exists, or if in some suitable defined sense, learning with errors or learning parity with noise is a hard enough super-bit generator. I won't go into details of these results, but these are the results that inspired our work. And you can see that both these results require some notion of hardness against non-deterministic algorithms, for example, NP not equal to co-NP or super-bit generators. So how am I doing on time? Okay, so do you have any questions so far? If no, then let me talk about our results and Rahul's concurrent results. We show that the hardness of range avoidance problem can be based simply on the existence of Demi-Bits generator. Previous work required super-bit generators with specific structure like LWE or LPN, but we found that actually just any Demi-Bits generator suffices. And Rahul Lango took one step further. He showed that if Demi-Bits, actually not Demi-Bits generator, but if the truth table generator is a Demi-Bits generator, then every circular bound, like relative to a random oracle, every circular bound is hard to prove. I'll explain what this is later, but first, I want to emphasize that the first bullet point is really a strengthening of the second bullet point, because proving circular bounds relative to random oracles, it can be reduced to some sort of range avoidance instance. And we just, like, the main theorem is that Demi-Bits generators imply hardness of range avoidance problem. But if you don't believe the existence of Demi-Bits generators, then you can also take a contrapositive view, which I find equally interesting. It says that if you can certify one string is not in the range of a generator, then you can certify a lot of strings that's not in the range of a generator.
Can you say a bit why the first bullet is stronger than the second bullet?
Oh, let me see. We showed that if the second bullet is that if there are Demi-Bits generators, then there are hard instances of range avoidance. And the first bullet is that if there are Demi-Bits generators, then a particular set of hard instances that is proving oracle circular bounds. It's a set of hard instances for range avoidance. Actually, there's some small details, because if you really want to work with circular bounds, then Rahul really needs the true stable generator be a Demi-Bits generator. Anyway, I think the first bullet is stronger than the second bullet in the sense that the reduction overhead is smaller. And you will see. Thanks for the question. And any other questions? Great. If no, then are you ready to look into proof details? Let me first talk about our proof. We show that if there is an algorithm, a deterministic algorithm for range avoidance, then we can break Demi-Bits. So you hand me a Demi-Bit. We want to break it. By definition, this means that we want to design a non-deterministic algorithm that takes a length L string as inputs and accepts a large fraction of such strings, but rejects any string in the range of G. And recall that we have what R2 is a deterministic algorithm for solving range avoidance. And actually, our argument extends to non-deterministic algorithms solving range avoidance. So these are algorithms that can guess a string and tries to prove that this string is not in the range. And if there is a valid proof, it can offer this string. It's basically equivalent to proof systems trying to prove one of the strings not in the range. But for simplicity in this talk, let me just assume the range avoidance algorithm is deterministic. What is the naive approach for doing this? Simple, right? Given y, you just see if the range avoidance algorithm on our generator outputs y. If it outputs y, then we are sure that y is not in the range. But the drawback of this is that our naive algorithm only accepts a tiny fraction of strings. So what do we do? It's very easy. We just add a hash function. Our adversary for breaking Demi-Bits generator first guesses a hash function from a certain pairwise independent hash family and compose it with G. You need to set parameters carefully so that after composing these two things, the output length M is still larger than the input length N. But this just needs a Demi-Bits generator with, let's say, linear stretch. And then we get a hash function, and we can just feed H composite G into our naive distinguisher. This at least satisfies the the bullet B in the sense that if some y is in the range of G, then hy is in the range of H composed with G. And if our range avoidance algorithm is correct, then it can never accept y. I also want to stop here to let you see that this argument only works for deterministic range avoidance algorithms, not for randomized range avoidance algorithms. Even if the randomized algorithm might have only an exponentially small error probability. This is because we rarely want a non-deterministic adversary that's always correct. And if it guesses H and then simulates the randomized algorithm, it needs to guess a random computational path of the algorithm, and maybe it guesses the wrong path. So at least so far, this looks good, but we still need to justify A. That is, our distinguisher B accepts a large fraction of random string. This needs some property of the pairwise independent hash function or universal hash function. So let me just quickly go through universal hash functions. These are a family of hash functions, and if you haven't seen this before, you can have a concrete example in mind. That is, every hash function is represented by a matrix over GF2, and the evaluation of hash function is just matrix vector multiplication over GF2. But there are also other ways to construct universal hash functions. The only property of such hash family we need is the so-called leftover hash lemma. And let me state one version, like one corollary of this lemma that is suited for our purposes. To state this corollary, let's consider an adversary that takes a hash function and an output of the hash function and tries to determine if the output is a truly random string or produced from the hash function. And let me stress that the leftover hash lemma is information theoretic. So the adversary here is computationally unbounded. And imagine that we have a sunglasses guy who has a secret string y, secret input y. And the sunglasses guy is either going to give you a random hash function and a random output, or it's going to give you a random hash function and the hash of y, where y is the secret string. We say that the string y pulls our adversary A if the adversary cannot distinguish between these two distributions with good advantage. And the leftover hash lemma just says that if we set parameters correctly, then with high probability over, fix any adversary with high probability over y, the adversary is 2 to the minus 2m fooled by a random y with high probability. And let me just emphasize that for our proof, we really need the advantage to be exponentially small in m. Any questions so far? Because this is, I guess, the most technical slide of my talk. Great. If there are no questions, then let's see why the leftover hash lemma implies that our adversary successfully breaks Demi-Bits. Recall that what our adversary did was just guessing a hash function from our universal hash family, and then running the naive adversary on hash function composed with G. So let's define the following adversary A prime. A prime of hash function and output is 1 if and only A on hash composed with G gives you the output. And you can easily see that A prime accepts a random hash function and a random output with probability exactly 2 to the minus m, because the probability that A of something, this thing is independent from Z. The probability that this thing outputs Z is exactly 2 to the m over a random choice of Z. And now, if I have a string y that's 2 to the minus 2m false a, then I can safely replace z with hash function of y, right? And we get that the probability or a random hash function such that a prime h and hy outputs 1 is strictly larger than 0. And this is the place where we really want the advantage to be exponentially small in m, and in fact less than 2 to the minus m. But what does it mean by this? By if the probability that over h that this thing happens is greater than 0, then in particular there exists some h that makes this happen, and our distinguisher will accept y when it guesses h, because a prime h hy is equal to 1 exactly means a of h composed with g outputs h of y, and this means our adversary accepts. And that completes the whole proof. The more complicated proof that I'll present in the talk. To wrap up, what we showed was that given a non-deterministic algorithm for the range avoidance problem, we can use it to break any Demi-Bits generator. And we do this by just composing the Demi-Bits generator with a hash function that we guess, and plugging it into the naive distinguisher. You can also see that the non-determinism is very crucial here, because we really need to guess a hash function. And in fact, we get the following theorem, which I think has a very nice form. If I have a Demi-Bits generator, then for every non-deterministic polytime algorithm trying to solve range avoidance, I can always find a hash function and compose it with this Demi-Bits generator so that our range avoidance algorithm fails.
By the way, so this non-deterministic algorithm for reading Demi-Bits generator is like the hash function you get also you can also not verify it works, right?
But we have just showed that the algorithm never accepts anything in the range.
Yes.
So what do you mean by you cannot verify it works?
Like when you fix a hash function, you cannot efficiently verify that it satisfies your condition. The condition A, like you need to accept more than half.
No, the condition A.
Condition B will always be satisfied.
Yeah, but condition A is for our distinguisher B. It has nothing to do with the hash function. I think condition A just says that for a large fraction of strings y, there exists a hash function such that this happens.
Yes. I'm just saying that you can guess this hash function, but
yeah,
you cannot prove that this hash function works.
Oh, you can just run A on H composed with G and verify that it's equal to Hy.
Oh, but you cannot verify that it accepts a large fraction.
I don't think there is a single hash function of H that will work for all Y or large fraction of Y. I think it's just say for a large fraction of Y, there exists a hash function, let's call it Hy, so that this happens. And you really need non-determinism to guess Hy. Thanks for the question. And any other questions? If there are no, then let me continue. If you know what is proof complexity generator, then well, this is equivalent to the existence of proof complexity generators against any proof system. And in our paper, we did some further work by showing the proof complexity generator has some stronger property called pseudo-surjectivity. If you are interested, welcome to check our papers. And then I'm going to talk about Rahul Elanco's proof. And the proof somehow uses the same technique as BPP in PH. Imagine that this is the space of every n-bit string. And imagine that we have a dense subset D of this n-bit string, which means that D contains a constant fraction of all n-bit strings. And if we have a n-bit string x, then we can shift the D by x by XORing any string in D with x. We get a new set which is still dense. There's a classical theorem proved by Lotman that shows that for any dense subset D, there are linearly many shifts x1 to xt, such that this shift of D covers all the Boolean cube. And this proof is really simple. You just pick the shifts uniformly at random, and every fixed point is covered by these shifts with very good probability very close to 1, and then you use a union bound. This was the core idea behind BPP in PH, and actually it's also the core idea in Rahul Ivangov's new proof. Rahul stated his proof as on probability of circular bounds. So I will also do the same thing. Although you can also refer his proof as hardness of range avoidance. Let's say that we want to prove if random circular bounds are hard, then every circular bounds are hard. This is like proving that if there are Demi-Bits, then range avoidance is hard. But we cannot quite do that. But let's see what we can do. Let's fix a proof system P, and assuming the true stable generator is a Demi-Bits generator, then P fails to prove a significant fraction of random circular bounds. So let D be the set of true stables that P cannot prove circular bounds for. And if true stable generator is a Demi-Bits generator, then D is dense by definition. And now let's choose random shifts x1 up to xt, so that these shifts cover all the Boolean cube. Then you can see that since P cannot prove circular bounds for D, P cannot prove any circular bound relative to x1 up to xt. Let me elaborate on this. Suppose we have an arbitrary true stable, and it was covered in some shift of D, so D XOR xi. This means the arbitrary true stable is equal to the XOR of some xi and something in D. If this true stable is in D, then P cannot prove lower bounds for this true stable, this lighter true stable. And suppose P can do some very basic reasoning about circuit complexity. That is, if the light true table is easy, then our heavy arbitrary true table that we start with is easy relative to xi. Suppose P can reason about this, then we can show that if P cannot prove this true table in D is hard, then P also cannot prove our arbitrary true table is hard relative to xi. Because otherwise, P can just prove this true stable is hard by first proving this is hard relative to xi, and then saying if this is easy, then this is also easy relative to xi. And so this implies that if the true stable generator is a Demi-Bits generator, in other words, if random circular bounds are hard, then relative to a random set of shifts x1 to xt, every circular bound is hard to prove. And since x1 up to xt are random, you can also say that if random circular bounds are hard, then relative to most oracles, every circular bound is hard. Any questions so far?
Sorry, can you just, I think you sketched it earlier, but can you say a little bit more about how this translates to a hard instance of range avoidance? I'm just wondering where this x1 through x2 is.
I see. So the range avoidance instance is a circuit that has x1 to xt hardwired, and then it takes as input a small oracle circuit where the oracle is intended to be x1 to xt. It outputs the truth table of the oracle circuit. So this is basically the oracle version of the truth table generator.
I see. So x1 through xt define a distribution over. Like, this is a randomness that defines a distribution over these range avoidance.
Yeah. And you can actually show that any proof system, if you insist on perfect soundness, then it will fail to prove any circular bound for most of the random oracles. Thanks for the question. Any other questions? Nice. And to wrap up, Rahul showed that if random circular bounds are hard to prove, then with hyperability over an oracle O, every O oracle circular bounds are hard to prove. And this is just by Lotman's shift. Actually, okay, here is how you translate this into hardness of range avoidance. If G is a Demi-Bits generator, then we can select a bunch of shifts x1 to xt and create a hard instance for range avoidance as follows. You just first, like, given input s and I, you first use s to generate a pseudo-annual string from the Demi-Bits generator, and then ship it with xi. For any non-deterministic algorithms, there, like with hyperability over the shifts, as this CX will be a hard instance for range avoidance for this non-deterministic algorithm. And I guess that's really all the conceptual and the technical things I want to talk about today. And as a summary, I believe that we are just out of the dark age of cryptography against non-deterministic adversaries, and I'm sure there are a lot more to discover. For example, we slightly extended the boundary of such cryptography to include hardness of range avoidance and also proof complexity generators. But maybe we can develop this further to shed light on the improbability of circular bounds, or some other implications for why complexity theory is so difficult. Perhaps complexity theory is difficult because of cryptography against the proof systems. And that's all I want to say. Thank you very much. Any questions?
Good question. Mentioned that some unprovability using Demi-Bits. Is there some result in the reverse direction? Like something why how we should believe that that's hard.
Like unprobability results imply Demi-Bits. Well, I'm not aware of that.
You didn't know.
Like any reason to believe Demi-Bits exist. Like for example, well, this is like I'm not super sure, but it seems that the truth table generator is a pretty hard candidate. Well, I think this is subjective. For example, any reason to believe wave functions exist. But I hope that after more research on these things, we will have a better understanding of whether Demi-Bits should exist or not.
Can you say that Demi-Bits exists provided that random stat is hard to refute or something? Like that?
Yes, I think
That's a
yeah, at least under like suitable parameters.
let's say you have a Demi-Bits generator with
Hmm.
one bit of stretch. Are there length extension theorems? Can you convert this into a generator that you can actually use in these proofs?
Well, there are length extension theorems, and they are proved pretty recently by Ido Samarit and Lu Mingzhang. But they only say that if you put a lot of Demi-Bits generators in parallel, then it's still a Demi-Bits generator. But we don't know if composing two Demi-Bits generators sequentially still gives you a Demi-Bits generator.
But both your proof and Rahul's proof require linear stretch, is that right?
Actually, our proof needs, but I think Rahul's proof only needs like super log stretch or something.
I see. So he can rely, so then he can rely on the length.
Yeah, I didn't check the details.
Okay.
I only know that our proof cannot rely on that.
Thanks.
Next question. Oh, and thanks for the question because it really touches some basic question about Demi-Bits that are still open.
There are any other questions? Let's say,